Connectivity. So we say a graph is connected. This applies both to undirected and directed. A graph is connected if there is a chain between every pair of distinct vertices in the graph. So if you can get from one vertex to another by following edges either forward or backwards. And in an undirected graph, it doesn't matter. Just follow edges. So disconnected graphs have more than, a disconnected graph has more than one what are called connected components. These are subgraphs which are themselves connected, and there are no edges from one component into another. They're connecting one component with another component. So let's look at these graphs. We've got three graphs here. G9, G10, and G11. Is G9 connected?
Yes.
Yes. Is G10 connected? No. How many connected components does it have?
2.
It has 2. All right. It has that one and that one. Okay. G11. Connected or not connected?
No.
Yeah, disconnected. So this is tricky because these edge crossings are not vertices. So how many connected components does it have?
2.
How many connected components does this have?
1.
1. Yeah. Connected graph just is one connected component, its own connected component. Okay. For a digraph, we have a stronger property called strong connectivity. So a digraph, in other words, a directed graph, is called strongly connected if there is a path from every vertex to every other vertex of the graph. So there has to be a path. In other words, if I have a vertex over here, U, and a vertex V over here, there has to be a path from U to V. Okay? But I can flip the roles of U and V, and I also insist that there is a path from V to U. So there has to be another path with edges going in the opposite direction of some length. So in other words, if you think of these as one-way streets, a graph is strongly connected if, starting from anywhere, you can legally drive to anywhere else. Basically, that's what a strongly connected graph is. Okay, digraphs. So, more terminology. A tree. A tree is a connected graph. Read undirected graph. A connected graph that has no cycles. So it has two properties. It's connected. So there's a path connecting any two vertices, and it has no cycles. A forest is a graph that has no cycles. This is just called an acyclic graph. So a graph that has no cycles is called an acyclic graph. It's also called a forest because it may not be connected, but if it's not connected, what can you say about its connected components? They are trees. Right? They are acyclic and they are connected. That's what a tree is. So the connected components are certainly acyclic. And they're connected, so they're trees. So we call that a forest. A forest is just a graph made up of trees. Is a tree a forest?
It's a component of.
It is a forest. A forest, just take the definition at its word. Okay? A forest is a graph that contains no cycles. Does a tree have no cycles? Yes. So it qualifies as a forest. Okay. You might say it's not a proper forest. It's a pretty puny forest. A forest with one tree. I mean, no one would call that a forest in real life. So if you have a graph G, a spanning tree is just a spanning subgraph of G that is also a tree. for G to have a spanning tree, it has to be what? It has to be connected. And that's the only restriction. If it's connected, it has a spanning tree. And if it's not connected, it doesn't. Okay. So, connected graph has... so let's go back for a tree. So trees are really nice. They have lots of... this is actually a pretty strong condition. So this says it's connected, so there's a path from any vertex to any other vertex. In a tree, there's always one unique path from one be connecting any two vertices. There can't be two paths. Why is that?
Because there would be a cycle.
Yeah, so if you look at the union of the two paths, there's got to be a point where they diverge and then they converge again. Go around that. That's a cycle. So, it looks like... if there's a path there and there's a path there from A to B, they're different. You can sort of just take the discrepancy, and that forms a cycle. Or it may form more than one cycle, but it certainly forms at least one cycle. So that's the thing. In a tree, there's just one unique path from every vertex to any other. There's only one way to go. Here's the other nice thing about a tree. If a tree has n vertices, some number of vertices, it has exactly n minus 1 edges. So it has one fewer edges than vertices. Always. If you have at least as many edges as vertices, you can prove that there has to be a cycle somewhere. So if the count of the edges is at least the count of the vertices, there has to be a cycle somewhere. If a graph has fewer than n minus 1 edges, yes, you can prove that it's not connected. It has to have at least two connected components. In fact, the number of connected components is exactly the difference between n minus 1 and the actual number of edges. That actually gives you the number of connected components. Only for acyclic graphs. I'll take that back. My bad. You could actually have more. All right. So which of the following graphs are trees and which are forests? This thing here, is that a tree?
Yes.
That is a tree. Is it a forest?
Yes.
Yes. Okay. Is that a tree?
No.
No. Is it a forest? Okay. Is that a tree?
Yes.
Is it a forest?
Yes.
Okay. Let me what if I add an edge there? Go back to there. That altered graph, is that a tree?
No.
Why not?
There's a cycle.
There's a cycle. Yeah. So A, B, E, D, back to A. Doesn't it looks like a hourglass shape. Okay. All right. Okay. All right. So we've seen two ways of representing graphs. As a picture with dots and lines, in regular set notation, which is kind of clunky and cumbersome and hard to read. Neither of those is particularly good for feeding graphs into a computer as input. So if you want to run algorithms on graphs as input. So we need to have some kind of representation for a graph. So we're going to represent graphs in two different ways. We'll represent it as an adjacency matrix. So we're going to always let n be the number of vertices. So n is the number of vertices, and m is the number of edges. This is actually pretty standard. the adjacency matrix is an n by n n by n matrix, all of whose entries are just either 0 or 1. And so it's going to be a square matrix, and the rows and the columns, there are n rows and n columns. You can think of the rows and columns as being indexed by the vertices of the graph. So if the vertices are, say, v1 through vn, then the first row and the first column both correspond to v1. All right, so if I'm in the ith row, if I look at the entry in the ith row in the jth column, I'll call that aij. Here's how you set it. aij is equal to 1 if ij is an edge in the graph, and it's 0 if it's not an edge. So this just tells you for every possible pair of vertices, is there an edge from the first vertex to the second vertex? So this works for a directed graph, yes? For an undirected graph, same thing, except that aij would be equal to aji, because it doesn't matter. But so that would be a symmetric matrix. But in a directed graph, aij may not be the same as aji. Okay, you could have ij might be an edge, but ji is not an edge. Okay, but the same matrix, adjacency matrix representation works for both kinds of graph. Okay, so we're just saying for every pair of edges, for every pair of vertices, is there an edge there or not? And that completely determines the graph, because that's all what a graph is. It's just there are some edges in there. And the ones just tell you where all the edges are. How many ones are in that matrix?
Same number of edges.
Same as the number of edges, right. Well, for a directed graph, it's the same number of edges. For an undirected graph, each edge is going to account for two ones, an aij and an aji. They're both equal to 1. All right. Incidence matrix. This is an n by m matrix. So the rows are indexed by the vertices, and the columns are indexed by the edges. And we just, if ij is an edge, then we put a -1 in the kth column. If this is the kth edge, so we list the edges now from, say, 1 to m. For the kth edge, if the kth edge is ij, then you put a -1 in the ith row saying that it's leaving I. And you put a +1 in the jth row saying it's entering j. And then all the other entries in that column are 0. Okay. This is for a directed graph. For an undirected graph, these would both be equal to 1. That's all you need to know about incidence matrices. In fact, we're not going to deal with them at all. So you can forget it. You can actually forget it.
Done.
All right. All right. All right. So write the adjacency matrix for this graph. Let's do this. And the way I like to draw the matrix is actually draw it as a table where you actually have headers to list what the vertices are. Instead of having a matrix there, it doesn't necessarily add up. Well, I'll do it in alphabetical order. So the matrix is just the entries in the table. So read it off to me. What's the first row? A to A is 0. A to B is 1. And this is undirected, right? So A to B is 1, B to A is also 1. So this is the from. I'm going from the row. So from B to A, this is the 2. Okay, so the row is where I'm coming from, and the column is where I'm going to. A to C. Oh, can't see the graph. A to C. 1. Oh, you can't. Oh. There we go. 1. A to D? 1. Okay. B to B?
1.
Yeah, because that's self-loop. But if we forbid self-loops in directed graphs, then that would be a 0. In fact, all the diagonal entries would be zeros for a directed graph. B to C? 1. B to D? 0. So I can fill this one in 1, 1. This will be 1, 0. How about C to C? 0. C to D? 1. So, and D to D? Okay. There it is. That's the adjacency matrix. Okay. Pretty easy. So you only need to store 1 bit per entry, so you can really compress this. Let's just skip that. Well, let me just say, what's the, you're going to have an entry, a 1 entry from A in the 8th row and dth column, and also in the dth row and 8th column. And from the bth row and 8th column, you'll have a 1. But in the 8th row and bth column, you'll have a 0. That's going in the wrong direction. So, for undirected graphs, the adjacency matrix is always symmetric. The values of the incidence matrix, well, forget the incidence matrix. All right, there's the adjacency matrix. That's just what we wrote down. Good. Without the headers. All right. So here's the adjacency matrix for the digraph, G16. Okay, notice it's not symmetric. It does not equal its transpose. Okay, there's the incidence matrix. Okay. All right. I don't think we really need to do this, right? Because we kind of already done it. I'm going to skip over this. Yeah, not good. Okay. And I'm going to skip over this. Let's do 4. Is the following subgraph a subgraph of G1? So let's go back to G1. There's G1.
It is.
Flip back and forth. Yeah, it's certainly a subgraph. Is it spanning?
No.
No. What's missing?
A.
Yeah, vertex A in G1 is missing in this. Okay. Is this a tree?
Yes.
Yes.
Is it a spanning tree of G1?
No.
All right. It's 5 after, and now we're starting algorithms. So this is a good breaking point. So let's stop now. Here we go. So I don't know what the schedule is when you come back. You don't know when you're coming back, do you?
I don't really have a good idea.
Okay.
In terms of, I don't know how long this is going to start, and we've gotten stacked in Alexander Hall and had to wait 30 minutes.
Yeah.
The last one took like an hour and a half.
You're back when you're back. Okay. All right.
Why do you have to be like that? Things down in Dave.
I said the last
This is a data down.
You know, the last one we sat there forever.
The last one was.
People were sleeping. Like, but the good news is,
Your phone apps don't require internet working on building. Make sure
when you're not internet,
we'll see what we see.
All right. See ya.
I'm taking my work.
Have a great time.
No, I couldn't take the press in with me. It's not a bad thing.
Not even hesitating on that. I know. I'll be mad. The entire time the kernel is on.
Turn this off.
Are you doing that too?
Yep.
Okay. I assume that's recording. All right. So now till 3 o'clock, we'll learn sort of 3 really fundamental graph algorithms. 2 of them do exactly the same thing. They just do it in a different way. The third one, Dijkstra's algorithm, is different. But they all have some similarities. So, minimum spanning trees. So imagine a graph, undirected graph. And it's going to be a network, so we associate with each edge some cost, some real valued cost. And the weight might mean length time, lag time, natural cost, etc. So a minimum spanning tree is a spanning tree, so the graph has to be connected. It's a spanning tree that minimizes the total weight. So the total weight meaning just add up all the weights of the edges in the tree, and that's the total weight of the tree. And what we like to do is to find a minimum spanning tree, one that minimizes the weight. So in general, there are lots of different spanning trees for a graph. They'll have different weights, and we want to find the smallest one. All right. Why do we want to do this? What's it good for?
The shortest path.
Hmm?
Identifying the shortest path.
It's not going to give you the shortest path necessarily.
Reducing the unnecessary.
Sorry?
The cheapest method to talk to everyone in that network.
Okay. Yeah, it's the cheapest method to allow everyone to talk to other people in the network. So you imagine that you've got a bunch of workstations, okay, and you want to wire them up so that there's a path from every workstation to every other workstation. That's a connected graph. But you want to do it as cheaply as possible, and every potential link between two computers that you draw carries a certain cost with it. I mean, some might cost more than others. Like some you might have to, go underground and come back up, or, So you want to do it as cheaply as possible. Or you want to lay a telephone network, fiber optic cable, as cheaply as possible so that everyone can talk to everyone else. Now, it doesn't mean necessarily they're going to be able to talk efficiently. It just means that there's some connection. It might be a long one between any two people. All right. If the edge weights are negative, then it's possible that if you could add negative edges to a minimum spanning tree and get an even cheaper subgraph, minimum spanning subgraph. We'll assume that we're looking for a tree. So if the edge weights are all positive, then the minimum spanning subgraph is going to be a tree. Why is that? Well, if it's not a tree, well, it's got to be connected, right? It's spanning. It has to connect everything, so it's got to be a connected spanning subgraph. If it's not a tree, what does that mean? It's got a cycle. If you have a cycle, what can you do?
Get lost in the loop.
Say what?
Lost in the loop.
Get lost in the loop. Well, okay. You can always cut a link out of a cycle without disconnecting the graph, right? I mean, because if you've got some cycle, there's a cycle, and you've got other stuff coming up. You can always remove a link that belongs to a cycle, and if the graph was connected before you deleted the edge, it'll still be connected afterwards, because any path from a vertex over here to a vertex over here that used that edge could just as easily bypass that edge and take a detour around the rest of the cycle. So it's still connected. So if you have edge weights that are positive, then any minimum spanning subgraph is going to be a tree, because you can always remove. So if you have a cycle, you remove an edge and keep doing that until you have no more cycles, and then you've got a tree. Okay. All right. Questions on that? So generally, we're looking for spanning trees. All right. So here is a graph. What's a spanning tree? Well, here's a spanning tree. So, no cycles, and it contains all the vertices, and it's connected. Is that a spanning tree? No, that's a forest, and it's not a tree. It's a spanning forest, but it's disconnected, so it's no use. All right, is that a spanning tree? No, it's connected, but it's got a cycle. And that you can remove any of these edges from the cycle, and you'll get a You'll get a spanning tree. Okay. All right. Two algorithms for minimum spanning trees. First is Kruskal's algorithm. The second is Prim's algorithm. And Kruskal's algorithm is ridiculously simple. I mean, it's almost like, you know, what a little kid would do. Okay, to try and find a minimum spanning tree. Well,
Yeah, I should be able to get
They're saying we can do it with this.
I'm saying that you.
Is there hope for me?
I didn't say anything.
But you did.
Yeah. All right. So here's what you do. You've got a graph. You've got a graph G. That's your input, and we'll assume it's connected. So here's one thing: if the graph is not connected, then there's no minimum spanning tree. In fact, there's no spanning tree at all. You will find that out in the course of the algorithm. Something will go wrong, and so actually you can use this as a connectedness test if that's all you want to know. Okay. So G is our input graph. And now what you do is you initialize another graph, a subgraph, T for tree, and it's going to have all the vertices of G. So it's a spanning subgraph, and it starts off having no edges. So it's just n isolated vertices. Okay, no edges at all. And then what we're going to do is we're just going to add edges to T until we get a minimum spanning tree. How do we add them? Well, first you make a list of all the edges in G and sort them in ascending order by cost. So the cheapest edges come first, and then the most expensive edges come last. Now you just go through the list one by one, take out an edge, look to see if I add this edge to T, does it form a cycle? If it does, you can't use it, throw it out. If it doesn't, add it to the tree. Just keep doing that. And then do that n-1 times until n-1 edges are actually added. Then what you have is guaranteed to be a minimum spanning tree. So this is a very, it's a very naive algorithm. You know, if you were going to add an edge to a minimum spanning tree, what edge would you pick? Well, you'd pick the cheapest one you could, and you just add it. Of course, you don't add it if it causes a cycle, because you don't want to do that. But if it doesn't, just go ahead and add it. This algorithm is an example of what's called a greedy algorithm. In a greedy algorithm, at each step, you do what looks best at the moment. So you take some locally optimal step. And the locally optimal step is choosing the next cheapest edge in the list. And it turns out the greedy algorithm, in this case, actually works. It actually gives you a correct tree. Okay. So get a lid. If there's a tie, when you sort these in ascending order, if there's a tie, if two edges have the same weight, doesn't matter what order they come in, just order them arbitrarily. Okay. So select an edge. If it forms a cycle, delete it, otherwise add it to T. Do this until T is a minimum spanning tree. So how do you know when to stop? That's the only question. Okay, once you've got it connected, how do you know?
Because there's a line to every dot, basically.
Ah, yes. One less edge than vertices. That's actually the easiest test. You know how many vertices there are? There are like 17 vertices. then all you have to do is count to 16. All right, just every time you add an edge to the tree, increment that count. When you've added your 16th edge, you know you have to have a spanning tree at that point. Because, why is that? Because it's acyclic. And it has to be connected, because if it's not connected, it's a forest. It has more than one connected component, and so the deficit of edges has to be more. Well, anyway, it's got to be a tree. So just count to the number of vertices minus 1, and then you're done. So we're going to run this algorithm. So that's Kruskal's algorithm. We're going to run it on this graph, on this network. Notice we label each edge with its edge cost. Okay. And we're going to build a tree, and the total cost of this tree is going to be 12. So you can make a list and write it out explicitly, or you can just follow along and look for what's the cheapest edge. BC, yeah, so that has weight 1. Okay, so here's the initial tree. It contains all the vertices, all 6 vertices, and no edges. So the edge set is empty. So in step 2, step 2, I create the list, and so BC comes first. All right, so step 3, I just keep adding edges to the tree. So the first edge, the first edge in the list is always added. Because the first edge you add in the tree, it's never going to cause a cycle. So it's always going to be added. So you add BC, and I am going to annotate that on the graph by making a squiggle. So that edge is now in the tree. Okay. So what's next on the list? AB. All right, has 2. CF also has 2, but we just arbitrarily put AB first for no good reason.
No,
doesn't matter. It's completely haphazard. You might get a different tree. So swapping the orders actually might give you a different tree. If that's the case, either tree will be minimum. So they'll both have the same minimum value. So minimum spanning trees are not necessarily unique. There may be more than one. All right. So, but the next one we pick out is AB. Do we add it? Does it form a cycle? No, so we add it, yes. There we go. Okay. So, there we go, AB. So what's the next edge? CF. So it turns out we're going to add it anyway. We're going to add both. So, all right. So we do add it because it doesn't form a cycle. There we go. All right. How many edges are going to be in this tree eventually? 5. Right? And we've got 3 already. So there's only going to be 2 more. What's next on the list? Well, AC is actually the next on the list. If I'm crossing off the list, I've crossed off that. Yeah, AC will form a cycle, so we just throw it away. Okay, and the next one is DF. That's good? Okay, so we'll put DF in. Cross it off. All right. BD. No. Yeah, forms a 4 cycle. Cycle with 4 edges. So, yeah, I don't want to mark that in. So BD is gone. CD. Yeah, no. CE. Where is he anyway? By that stupid thing. Okay. All right. So CE? Sure. there's our 5 edges.
Awesome.
And at this point, we can stop and forget the rest of the list. There's the list. The list might be really long, and we just stop. Right? And we found it. All right. And if you count up the edge weights, you'll get 12. This actually turns out this is the only minimum spanning tree. There are no others in this particular graph. That's not necessarily the case always.
This algorithm,
Yeah.
right? Because there are other spanning trees using other algorithms, right?
There are no other minimum spanning trees using any algorithm. This is the only tree. This is the only spanning tree of total cost 12. So even if you just exhaustively search over all possible spanning trees, you'll never find another one of cost 12. Yeah. So it's not just the algorithm. It's there really is only one tree. The proof of that is not worth going into. You can, trust me. Try it at home.
Challenge.
Challenge. Captain Langley, do you have a question?
No.
Oh, okay. All right. Was that ridiculously easy? Say yes. Okay. When you actually implement this on a computer, there's a technical glitch. Well, it's not a technical glitch. I'm going to say there's something non-trivial that has to happen. The computer has to decide when an edge will form a cycle and when it doesn't. I mean, when you run it on this graph, it's easy to see just by inspection that you formed a cycle, that you would form a cycle or not, just by inspection. But that's you can't. A computer doesn't go by inspection. A computer has to have an actual algorithm. And there are fast data structures whereby you keep track of clusters of edges. You actually keep track of the connected components. And every time you draw an edge, so Kruskal's algorithm the first edge could be over here, and then the next edge could be way over here, and then the third edge is over here, and then over here, and then over here. And in the middle of this thing, generally you have a forest. You have a bunch of connected things. And what this data structure is, it's called a disjoint set system or a union-wide data structure. It keeps track of the connected components for you. And every time, and what it can do is, given two vertices, it can tell you whether or not those vertices are in the same connected component. If they are, then putting an edge between those two vertices is going to form a cycle, because they're already connected by a path. So you can't do that. On the other hand, if they're in different connected components, then it's safe to add that edge. You're not going to form a cycle. And when you put that edge in, the data structure allows you to then merge those two connected components into one connected component as far as the data structure is concerned. So you update the set system as you go. And these set system operations are very fast. Okay, they're practically constant time per operation. The bottleneck here, the thing that actually takes the most amount of time in this algorithm, is sorting the edges. That actually takes the lion's share of the time of this algorithm. Once you've sorted the edges, then you've done most of the work. All right. Any questions on Kruskal's algorithm? Okay. So you could do it by hand, by inspection, no problem. No. So there we go. And there's our spanning tree. Yes, it looks the same. Okay. All right. The second algorithm is Prim's algorithm. It does the same thing. It finds a minimum spanning tree, but it does it in a completely different way. Well, not entirely different. It just, you'll see. So what Prim's algorithm does is you initialize the tree to just being a single vertex in the original graph and no edges. And You can start with any vertex. Doesn't matter. You'll get a tree eventually. Every spanning tree is going to include every vertex, so it doesn't matter which vertex you start with. All right. Now, here's what you do. You now select an edge with the smallest cost from those edges that go from a vertex that you've included in T to one that you haven't yet included in T. So T is going to contain a set of vertices. It just has one vertex to start with. But in general, T will be a set of vertices, and you look for the cheapest edge that goes between a vertex in T with a vertex not in T. Okay, that actually crosses the edge from being in T to being outside T. Take that edge, add it to T, and throw in the other vertex on the other side. Throw that into T as well. So you've kind of grown T. So T has sprouted a branch that goes out this way. So what you do is you start at one vertex, you might call the seed, and now the tree just sort of grows out from that vertex. And at any time in the algorithm, you have a single tree which consists of part of the vertices, some of the vertices of the original graph. And you gradually expand this by adding another edge and the vertex on the other side. Keep doing that. Again, do this n-1 times, where n is the number of vertices, and then when you're done, you have a minimum spanning tree. So, let's see. So as soon as you get a spanning tree, stop. Otherwise, repeat step 2. So now, let's do that. Let's do Prim's algorithm on the exact same graph. Excuse me. And let's see, where are we going to start? I forget where we're going to start, so let's see what the slide says. We start at C. Completely arbitrary. Just pick a vertex. So we're going to start at C. So here's what T looks like to start with. It just contains C, and there are no edges. But what I've drawn is a border around, so what's inside T and what's outside T. So what's inside the circle is T, and what's outside the circle is not in T. So now what you do, step 2 says, look for an edge crossing this border. So it has to cross the border somewhere. That's cheapest. Look for the cheapest edge that crosses this border. What is that edge? Yeah, BC or CB, doesn't matter. It's undirected. Okay. Algorithm says add that edge and the vertex on the other side, which is B. Add that to the tree. So here's what I'm going to do. Maybe I can erase. I erased everything. That was not what I wanted to do. Well, I can erase everything. There we go. Whoops. So there's the tree now. Okay. Step 2 again. What's the cheapest edge that goes from a vertex inside the circle to one that's outside the circle?
A, B, or CF.
A, B, or CF. Those are both weight 2. Okay. So, as with Prim's algorithm, if there's a tie, you can just choose one or the other arbitrarily. It doesn't matter. So, what do? We add AB again. Oh, well, okay. Boring, but all right. So we're adding AB. So now, I'm going to erase this. Wow, I erases everything, doesn't it? So there's our tree now. And notice that the edge AC is no longer possible to add. It's not actually part of the tree. Actually, let me put in the edges as well.
Since A and C are both in T, They would never try and add another link.
That's right. Exactly. A and C are in T already. They're both in T. You can never add the edge AC. And it will form a cycle if you do. So, all right. So there's the current tree, and those are the edges. So I circled the vertices. Those are the edges. What's the cheapest edge now from inside to outside?
CF.
Yeah, CF. So we're going to add CF. So now, this is good. I just erased everything. And now I've got this thing. I've got that. Okay. Now what? D. So there's only two outside. There's D and E, and I see an edge 4, 5, and 3. Okay. All right. I see 2 4 edges and 3 4 edges actually. But yeah, it's DF. It's the only weight 3 edge. So that's going in next. So now the tree is everything but E, and it's okay. So what's next? So there are 2 edges left. One has weight. Oh, I crossed it out. One has weight 4. That's CE, and the other one has weight 5. Or sorry, 6, which is ED. So I got to add CE. Okay. So now at this point, I guess I didn't have to do that. Now I'm done. I got everything there. Notice I got the exact same tree as before. Okay. Actually, I think we actually added the edges in the exact same order as in Kruskal's algorithm. That's pure coincidence. Usually it doesn't happen. Because in Kruskal's, as I said, at some point you have some forest. Whereas in Prim's algorithm, you always have a tree. It's not a spanning tree, but it's a tree of some subset of the vertices. So in general, you don't add the edges in the same order in the 2 algorithms. All right. Questions on any of that? Okay, so that'll do it. So this is also greedy, right? How is it greedy?
It's only looking at what's going on right at what you have.
Yeah, so you're doing this, it's working incrementally. And at each step, you're looking, okay, the tree is not a spanning tree, so I've got to grow it out somehow. Well, what looks like the best thing to do at the time is to pick the cheapest edge you can to grow it. That's the greedy part. Or I guess it's the chintzy part. It's the cheapskate algorithm. Thrifty. Okay. All right. Any questions on that? Okay. Let's see. Yeah, so we get the exact same graph, same cost. Okay. So here's what I'd like you to do, and then we'll take a break. Use Kruskal's and Prim's algorithms to find minimum, it should be minimum spanning trees for the following graph. Yes, question.
That 2, is that from C to B, or is that from...
Oh, yeah, there's one missing, isn't there?
Thank you. I'll take an extra point off. Thank you. That's what I'll earn, probably.
Let's see. All right, I'm going to make this 6.
Okay.
So E to C is 6.
Ooh.
So Kruskal's doesn't just starts wherever. For Prim's algorithm, I'd like you to start at B. Start at B.
Yeah, do both. Outside of like routing protocols, Dr. Fenner, do you think of any other like real applicability of these as far as we would be concerned?
Oh, for
I mean, I understand like
Yeah.
looking at it and looking at like the ways to get somewhere,
Right.
that type of stuff. But
I couldn't think of anything specific. I think it's just part of the overall engineer's education, I guess. Sometimes optimization is easy. In this case, it is. Sometimes it's hard. Haven't got a minimum spanning tree yet. Just say bingo when you go.
bingo.
Does that mean we win money?
Yeah.
Yeah, that's completely wrong. But I appreciate the effort.
All right. Well, all right. Let's do cross call, shall we? Let's do that first. So, what edge do I add first for cross call?
BC.
Tell me what to add. BC. Okay. Good. What's next?
CD or BE.
Yeah, BE or CD. So again, it doesn't matter which. I'll get a minimum spanning tree, and in this case, it's not going to affect the tree because I'm going to wind up adding the other edge anyway, in the next step. So, all right, let's add BE first, and then CD. Because neither of them forms a cycle. Now what?
Either AB or AC.
Yeah, either AB or AC or AE. Sorry,
Or AE.
AE. Now notice there's a tie. You can pick either one, and you will get a minimum spanning tree, but you'll get a different tree depending on which one you take. So I don't care. Let's do AB. Okay. There's 4 edges, 5 vertices. We're done. All right, that's a minimum spanning tree. What's its cost? 8.
Yes.
Good. Okay. All right. Questions on cross call? All right. Let's do prim. Okay. And I said start at B. All right, so here's B. BC. That's going to, right, okay, so that's the cheapest. So, I'll tell you what, I'm not going to erase. I'll put the edge in, and then I'll just extend that. How's that? Okay. All right. Now what?
Either CD or BE.
So either CD or CE.
B.
B.
Not CE. CE 6.
Oh, right. Sorry. Yeah, CD6. Okay. Yeah, either BE or CD. Let's do it. Okay, it doesn't matter. Let's do CD this time, just to be perverse. Okay, so that gets in. Okay. So that's what it looks like now. Now what?
BE.
Now BE. Okay. So when I add BE. Okay. Now A is only left, and again we're faced with the exact same choice. We have a tie for cheapest edge. And let's just do it the other way. Okay, AE. And now everything. All right. Questions? All right.